Okay, so why do I think that this is a quantum particle here? Well, I'll just name a few quantities that it's in touch with. First one here, that short one there, is power. So it's in touch with that. The longer one, power by the way is usually a watt. The watt is the watt. That's current, L3 over T3, which is the amp. Force, L4 over T4, which is the Newton. The total length there is just L over T, which is V over C. Now notice these are all actually can be just referred to in terms of B. So you got B, then you got B squared, then you got B cubed, then you got B to the 4, then you got B to the 5. 2, 3, 4, 5, and you'll notice that radius is irrelevant, it cancels out. So you just put a C on to put it into manually made units. Like for B squared you just put a C squared. For velocity you just put a B and a C. Okay, so that's voltage by the way, the C squared I forgot to mention. L squared over T squared, that's that length there. Again, I could have put it here. It's also in touch with that quantum particle. So it's all in touch with that quantum particle. And then if we look at that's angular momentum, which is L5 over T3. It's often just a curly L. This quantity here is energy, but when I say energy I'm referring to the joule. I'm not referring to EV. EV is actually for voltage, which is this one. Should have made that yellow by the way, because it goes from 0 to 1. And momentum, linear momentum, that's here. So that's L4 over T to the 3, and that's usually a little p, which I think stands for pole, because of this formula. The magnetic constant times the two poles over the radius squared equals the magnetic force. So, and notice that's that's actually like spin. You've got angular momentum, you got torque, which is the joule, and you've got linear momentum. So anyway, something's definitely spinning off that way. And because special relativity replaces the magnetic field, you can still put the magnetic field in, but it only goes in and out of the page. So if this was the right hand rule, I'd put my thumb that way and it would be curling that way. So if I was to make that coming out of the page, I'd do it like that and say that that's going into the page like that. And if there was another right hand particle heading off this way, again use your right hand, curl it around, you find that magnetic field is coming out and going in like that. And then notice you've got these magnetic fields heading in opposite directions, which means that they'll attract each other, and so that could be the reason why these actually start coming together. They've got the same spin. Anyway, back to this the position of this particle, which I'm saying is here, quantum particle. So it's got spin, it's also got a Poynting vector, which is this little quantity here, which is often denoted by a S like that, and its unit is L cubed over T to the 5. The longer one here is actually current density, which is that, which is often, I think, what is it? Is it the little curly p? Maybe. And here we've got acceleration. 3 types of acceleration. You got L over T squared, that's centripetal acceleration, which we call gravity, and then you've got your proper acceleration, which is that one down here, which is a curly A, which is 1 over T squared. And then you've got this current density can also be thought of as tangential acceleration. Normally tangential acceleration is given the same units as centripetal acceleration, but I think that's wrong. I think it's actually T cubed, not T squared. Okay, so here it is, your particle in touch with everything that's going on. That length there is the H field, which is T squared over, L squared over T cubed. So it's up here, the same H field. That one there is the magnetic field. Add them together, get your overall B field. Magnetic density, which is 1 over T. And now there's a difference between fermions and bosons in that the wavelength of a boson is proportional to its velocity. So I did that thing before where I had a constant frequency, and then it takes off, wavelength gets bigger, and then it slows down and the wavelength gets smaller. So it's actually directly related to that B, which is you can think of it as boson, B for boson, but it's actually V over C. Whereas the fermion uses de Broglie's wavelength, and that's that one there. So that's a fermion, and because in that case, as the velocity increases, its wavelength decreases because of length contraction, and of course the frequency goes flying up, and that's why it can't exceed the speed of light. A fermion can't even get to the speed of light without becoming a photon, which is a boson. Okay, so anyway, that's why I think that this is a quantum particle in the future, and its clock has moved ahead by 0.6. This is also space-time, so it's heading through space-time on that geodesic, you could say. That's a geodesic, and it's just, so it's got velocity and it's heading through space-time. Time is down here, of course.